Alright, hello. So we are going to go over the check for understanding questions for section 3 on relative velocity and then do a couple of examples. So this section is pretty short. So number 1, what does it mean to say that motion is relative? So what we're looking at in this section is, for example, let's say that you are on a bus that is traveling at a certain speed relative to the road, and then you are walking forward or backward on that bus, so you also have a speed relative to the bus. And so when we say that motion is relative, it's really just based on perspective. What are we referencing your motion to? Are we referencing your motion to the bus? Are we referencing your motion as compared to the road? And so that's kind of what we mean when we say relative. So at the beginning of the year, we talked about how, let's say you're sitting in a chair and you're not moving relative to the ground, but maybe you are moving because you're on planet Earth, and Earth is revolving around the sun. Okay, so the relative part just means in reference to what other object. Okay, so for relative velocity, there's a general equation. And so the velocity of object A as compared to object B plus the velocity of object B as compared to object C is equal to the velocity of object A as compared to object C. So for example, if we were talking about your speed, so this would be you in relationship to, let's say, on a bus, and then this would be the speed of the bus in relationship to the road. If we wanted to know what your speed was in relationship to the road, so A again being you and C being the bus, or no, sorry, road. Okay, then we would add up your speed relative to the bus and the bus's speed relative to the road, and that would give you the overall speed of you relative to the road. So that's the overall equation. So we're going to do a couple examples that use this with different objects. Okay, so for number 22, you are riding in a bus moving slowly through heavy traffic at 2 meters per second. So the velocity of the bus to the road is 2 meters per second. And you hurry to the front of the bus at 4 meters per second relative to the bus, so the velocity of you to the bus is 4 meters per second. The bus is traveling forward, you're moving forward, so the signs should be the same. And they want to know what is your speed relative to the road or the street, so velocity of you to the road. Okay, so overall, velocity of A relative to B plus velocity of B relative to C equals velocity of A relative to C. So let's do that. Velocity of A to B is u to the bus. So velocity of u to the bus plus the velocity of, since B is the bus to C, which is the road, velocity of the bus to the road equals velocity of A, which we said was u, relative to the road. So that's the one we're trying to solve for. Velocity of u to the bus is our 4 meters per second, plus the velocity of the bus to the road is our 2 meters per second, and that's going to equal a total of 6 meters per second as your velocity relative to the road. Now, let's look at the next one. Okay, so number 23. Rafi is pulling a toy wagon through the neighborhood at a speed of 0.75 meters per second, so velocity of wagon to the road is 0.75 meters per second. A caterpillar in the wagon is crawling toward the rear of the wagon at a rate of 2 centimeters per second. So velocity of the caterpillar relative to the wagon is negative because it's going the opposite direction towards the rear of the wagon versus the wagon going this way. That's negative 2 centimeters per second. And they want to know what is the caterpillar's velocity relative to the ground or the road, since that's what we're using. So velocity of the caterpillar relative to the road, that's what we're solving for. So velocity of A relative to B plus the velocity of B relative to C is equal to the velocity of A relative to C. So let's see, velocity of the caterpillar to the wagon, so caterpillar is going to be A, wagon is going to be B, plus the velocity, B is the wagon, C is then the road, equals the velocity of the caterpillar with reference to the road or the ground. Okay, so before we can plug this in, our units are different. We have centimeters and meters. So I know there are 100 centimeters in a meter, so I'm just going to move my decimal 2 spots, so that gives me negative 0.02 meters per second. Now I can plug that in here, make it negative since he's going the opposite direction. Plus the velocity of the wagon with respect to the road is my 0.75. And that's going to equal my velocity of the caterpillar with respect to the road, which since this is negative, that's going to give me 0.73 meters per second. All right, let's look at number 24. Okay, a boat is rowed directly upriver at a speed of 2 meters per second relative to the water. Let's say that we're going that direction. So velocity of boat to the water is 2.5 meters per second. Viewers on the shore see that the boat is moving at only 0.5 meters per second relative to the shore. So the velocity of the boat to the shore is only 0.5 meters per second. So right away that tells me he's probably rowing like against a current. What is the speed of the river? So we want to know velocity, that's not a V, velocity of the water with respect to the shore. Okay, so velocity of A to B plus velocity of B to C equals velocity of A to C. So let's make velocity of A to B, boat to the water. So velocity of the boat to the water plus, okay, so that means that B is the water. Velocity of the water to the shore then, so C is the shore, is equal to velocity of A, which was the boat, and C is the shore. Okay, so velocity of boat to the water is our 2.5 meters per second, plus velocity of water to the shore, that's what we're solving for, and that's equal to velocity of boat to the shore, which is 0.5 meters per second. So velocity of the water to the shore is going to equal, we'll subtract this to the other side. So that's going to give us negative 2 meters per second. And so the next part of the question was, is it moving with or against the boat? Since this is negative and the velocity of the boat is a boat to the shore and water is both positive, then I would say that this means that it's moving against. And that makes sense because the boat to the shore was smaller, meaning it's rowing against a current. Okay, so all the ones that we've looked at so far are where everything's in the same dimension. So now let's look at something that's not. So an airplane flies due north at 150 kilometers per hour relative to the air. So this is my 150 kilometers per hour, and this is the velocity of the plane to the air. Okay, so then there's a wind blowing at 75 kilometers per hour to the east relative to the ground. So let's go east, and this is air or wind relative to the ground, and that's equal to 75 kilometers per hour. And so we want to know what is the plane's speed relative to the ground. So we want to know velocity of the plane to the ground. Okay, so just like before, we could add these up, but the only problem is that they're not in the same direction, and so we need, or in the same dimension, and so we need to use Pythagorean's theorem to add them instead of just adding them in the traditional sense. Whoop, got it. Okay, so since we want to know the hypotenuse, let's call that R. Let's call one of these A, and let's call one of these B, and so we know that R squared is equal to A squared plus B squared. So R squared equals my 150 squared plus my 75 squared. And so then if I square these and square root everything, then I get that R equals 167.7 kilometers per hour. And we could also find the angle if we wanted to. Okay, but overall we just want to know the speed of the plane to the ground. So with these different winds, it's going to affect it either in a positive way or a negative way. Alright, so we'll go over any questions that you have in class. Otherwise, have a good day.